So the context for this problem is that Jacob is a basketballer and he knows the chance of him shooting a basket on any one shot is 0.6. So this is a binomial distribution question, isn't it? Because we have independent events. Each shot is 0.6, 60%. It's either a success or a fail. The basket is shot or it's not. So we have a binomial distribution. So I can start my solution by going x is distributed binomially with, and we've got to put two factors in here. We've got to put the number of trials and the probability of success. We already know the probability of success, it's 0.6. Now, further reading of the question down here is find the number of shots he would need to take to be more than 80% sure he will shoot at least one basket. So in other words, we need to find the number of trials that, because one trial would be a shot at the basket, right? So we need to find n is the unknown here, in order for there to be at least one basket. Okay, so that's the setup. We are given a target to aim for, and that is the 80% sure. So we want the probability to be 80% or greater, and that there's at least one basket in that number of trials of n. Okay, so what does that mean? That means that we are looking for the probability that x, the random variable that describes the number of times a basket is scored. We want the probability that x is greater than or equal to 1 because it's at least one basket. We want it to be equal to 0.8 for some value of n that we haven't worked out yet. So that's the setup. I say equals and not greater than or equal to. I could have put greater than or equal to there because it does say more than 80%. But effectively, if we set it equal to 0.8, that gives us our boundary value. Anything above that would be appropriate, right? So that we do this to work out our boundary value for n, and then we bump it up a bit to say, well, anything above that would be more than 80%. Okay, cool. Now, there's one other key phrase that really should be looked at when we have a probability question, and in it, the two words at and least are next to each other, are in there somewhere, then you should be thinking, is this better done as a complementary event? And the answer is yes, it is. In this instance, it not always is, but it is. So at least means look at the complementary event to see whether it would be worked out more easily. So what we could do, if we sort of didn't see that, you could, of course, just put in numbers for n and see what happens. So what's the probability of x greater than or equal to 1 when n equals 10? And it gives you a value. Oh, that's too high. Let's make n equal to 5. Oh, it's still too high. So you could do trial and error, but of course that's A, not very satisfying, and B, very inefficient, particularly when n might be, say, 117 or something random like that. So it's not a great way of doing it, but technically you could do it by trial and error if you had to. And by that, I mean putting it into your calculator. Using complementary events gives us a much more efficient solution. If the probability is that x has to be greater than or equal to 1, then the complementary event, what's the opposite of being greater than or equal to 1? Well, less than 1. And what does less than 1 mean? It means that there were no shots in. So that means that that would be the probability that x is equal to 0. Now, this is good news, and I'll explain why in a second, but let me finish the rest of it off. The complementary relationship, of course, is it's the probability of the complement taken away from 1, like so. So we've got this, the 1 minus the probability of x equal to 0 must be 0.8, because these two expressions are identical. Now, if this and this must be 0.8, then I'm hoping it's not too much of a leap of logic. Then what we simply need to do, our related question, I suppose, is if I can find a probability for x equal to 0 equaling 0.2, or maybe a bit less than 0.2, but 0.2 is what our target, our boundary value is. If I can find that out, then I am good to go. All right, so that's the main setup. Why is this good news? Well, it's good news because if I have the probability of x equaling a particular value like this, I can use my probability formula to figure that out. So if I go to my information sheet you'll see under binomial distributions, we have this old formula here. The probability of x equals little x equals nc little x, p to the power of x, that's the success 1 minus p, which is failure, to the power of n minus x. Let's have a look at that in context of this problem. So that means that we have n, the thing we don't know, c 0, and then we have the probability of success 0.6 to the power of x equals 0, little x equals 0, so that's to the power of 0, and then the probability of failure, which is 0.4 to the power of n minus x, and n minus 0 is just n. So we have that as our equation. Nice. Now, let me unpack each bit of there because your calculator won't exactly tell you this. NC0. So remember this, if you think about it logically, there's lots of ways you can do it, but if you think about it logically, it's like how many ways can I choose 0 from a set of n? And the answer is 1. By not selecting anything, I get my match. So NC0, anything C0 is always equal to 1. It's one of those facts that you just want to be able to remember. Anything to the power of 0 is also 1. So we've got 1 times 1 multiplied by this. So we've got 0.4 to the power of n. Okay, a lovely jubbly. Moving on then, since our target boundary was 0.2, I'm saying that 0.4n is equal to 0.2. Then I can use my log laws to go n is equal to log base 0.4 of 0.2, which then becomes a calculator operation, which is over here, and I go control log 0.4 is 0.2, and I get 1.756. 1.756, like so. Now, of course, Jacob can't take 1.756 shots. So what Jacob will do instead is Jacob will need to take at least 2 shots to be 80% sure. Okay, so that's it. That's basically it. There's an 80% confidence of getting one in as long as he takes 2 shots. It'll be 60% for 1 shot. That's basically it. Now, if you forget your log laws or that step there, you can of course use solve. Should get me the same value. So if I go menu, algebra, solve, and then go 0.4 to the power of n is equal to 0.2 with respect to n, and press enter, I get, of course, you'd expect exactly the same value again. So either way, using the solve on your function or just remembering your log laws so you can go straight to it, with whatever floats your boat, that's the way to do it. Hope that all makes sense.